Linear algebra was my gateway into proof-based mathematics, but it's rarely as straightforward as we see in class. Where it occurs, the linear algebra is often quite subtle. Let me show you one of my favorite such applications. Maybe it'll help you spot the tricky beast where it may appear as well. The problem takes place on the nodes and edges of an n-dimensional hypercube. You're probably familiar with a cube, which is a 3-dimensional hypercube, so called because each node has 3 incident edges. Generally, the n-dimensional hypercube has n edges incident to each node. It can be constructed by taking 2 copies of the n-1 dimensional hypercube and adding an edge between the duplicated nodes. Here are the first few hypercubes. Notice that the number of nodes doubles each time, so the n-dimensional hypercube has 2 to the n nodes. This structure also goes by the name Hamming cube, so called because it captures the notion of Hamming distance. Okay, let's back up a little. When used casually, the distance between 2 points means the length of the line connecting them. Using a little ancient Greek geometry, we can write the length as a function of the coordinates. This is Euclidean distance, or the distance as the crow flies from one point to the other. What if we're not a bird but a taxi on the busy streets of Manhattan? The length of the path that the crow flies doesn't work anymore. Instead, we should count the number of streets and avenues traveled. This is called the Manhattan distance, and we can also write this distance as a function of the coordinates. In some ways, the Manhattan distance is simpler than the Euclidean one since we don't have to compute squares or square roots. The Hamming distance is simpler still. We no longer care how much 2 points differ in each direction, only whether they differ or not. So the Hamming distance of 2 points is simply the number of coordinates in which they differ. This distance is often used to compare binary strings in information theory and strings of base pairs in DNA. In the Hamming cube, we label each node V by a point in n-dimensional space. Since we only want to know if the coordinates are the same or different, 2 choices suffice. Let's say plus or minus 1. 2 nodes U and V are connected by an edge if their points differ on exactly 1 coordinate. When U and V are connected by a path of length k, they must also differ on exactly k coordinates. This is the structure underlying the n-dimensional hypercube. Phew! After all that setup, we're ready for the problem. Suppose every node of an n-dimensional Hamming cube is a sleeping person. At the start of each round, you can poke someone and they'll wake up at the end of the round. Everybody who is awake at the beginning of a round will wake up all of their neighbors at the end of that round. How many rounds does it take until everybody is awake? Well, let's try a few simple strategies. On the first round, we could wake up the all ones person and then do nothing on the remaining rounds. The all ones person is awake at the start of round 2, so wakes up all of its neighbors. Its neighbors are awake at the start of round 3, so will wake up all of their neighbors, and so on. The person farthest away has coordinates which are completely different from the starting node of V. We call it the antipode and will denote its vector with a bar on top. If a circle went through all the nodes, V and its antipode would be endpoints of a straight line through the origin. The Hamming distance between any node and its antipode is exactly n, so it takes n rounds to wake up the antipode after the starting node wakes up. In this strategy, the bottleneck is clearly the antipode of the starting node, or the all negative ones person. Let's try to fix that. Again, we'll wake up the all ones person on the first round. Then, on the second round, we'll wake up the all negative ones person. Now we wait. This strategy wakes everybody up in the ceiling of n/2 plus 1 rounds. That's a bit of a mouthful, so I'll call it lambda. When I say lambda, I mean... Notice that everyone is at Hamming distance at most lambda minus 1 from the all ones person, or at Hamming distance at most lambda minus 2 from their antipode, the all negative ones person. Can we do better? Now the bottleneck seems to be the people with an almost equal number of plus and minus 1s. Maybe it'll help to poke some of them as well.
No, you cannot do better.
You can talk?
I got tired of waiting for you to find me, so I came to see what all the ruckus was about. Anyway, focus on the problem.
Well, I guess that's pretty surprising. If lambda rounds are necessary, then surely we can take advantage of other rounds to poke a lot more people. These people would wake up earlier, and they, in turn, could help wake up their neighbors earlier. And then their neighbors could wake up their neighbors earlier, and so on. But none of that helps?
No! And to prove this, you will need my help. First, let us make sure the goal is clear.
We want to show that lambda rounds are necessary.
Yes, how might the Hamming distance between the waking and sleeping nodes play a role?
Well, whenever a node is awake, it broadcasts its wakeful state to all of its neighbors. Generally, all nodes at Hamming distance k away will wake up in at most k rounds, but we can also think of this from the perspective of the sleeping nodes. If any one of their neighbors wake up, then they must also wake up in the next round. Generally, if some node at Hamming distance k away wakes up, then our node will wake up in at most k rounds. So, in order to show that lambda rounds are necessary, we need to show that some sleeping node is far away from all the nodes which are already awake, at least for a little while.
Good. More precisely, suppose I told you that by poking nodes v1 through v lambda minus 1, I could wake up all the nodes. How would you show that I was lying?
I'll need to find a node v star which is far away in Hamming distance from all the nodes in your list. In particular, its distance to v1 must be at least lambda minus 1, its distance to v2 must be at least lambda minus 2, and so on.
Right.
But how do we find v star? It's going to depend on v1 through v lambda minus 1, and they could be anything.
Yes, but do not despair, for I am here. Try to relate the Hamming distance of a pair of points to their inner product.
Alright, let's deal with v1 first. The Hamming distance between v star and v1 is the number of coordinates in which they differ, while the inner product of v star and v1 is, well, the sum of the products of some terms.
Do not forget that those terms can only be plus or minus 1.
Right, that limits what the product can be. If the coordinates match, then the product is equal to 1. Otherwise, their product must be negative 1. Thus, the sum is exactly the number of coordinates where the two vectors match minus the number of coordinates in which they differ.
Yes. Let us apply some algebra to obtain this. This first term is equal to n because a coordinate can only be the same or different. Generally, we have this.
Ooh, we want to show that the Hamming distance between v star and vi is greater than or equal to lambda minus I, which is the same as this inequality. Well, the Hamming distance is an integer, so we can just drop the ceiling function. It doesn't matter when n is even, and when n is odd, the largest integer less than the function with the ceiling is the same as the one for the function without. Plugging this inequality in for the inner product, and we get this. So that gives some constraints on what v star can be, but it still doesn't tell us how to find v star.
For that, we'll need to go into the null space. First, let us tidy up a little. Group together the lambda minus 1 vectors representing the list of people that we plan to poke as rows of a matrix A. We want to find a vector v star such that this is true.
Wait, if n is odd, there's an issue. V star is a vector with entries plus or minus 1, as is the first row of A. Their inner product will never be 0. If both vectors are all plus 1s, then their product will be odd. Whenever we flip the sign of a coordinate, the inner product is always increasing or decreasing by 2, so we can never get any even number.
That is right. Their inner product will always be an odd number between n and negative n. Let us omit the first row of A for now. We will simply try to find a vector v star such that this inequality holds. Before doing so, let us consider the simple case of a 2x3 matrix. B. What can you tell me about this inequality? where the coordinates of v star are plus or minus 1.
Well, v star is the corner of the cube and must live in the intersection of the half-planes defined by the rows of B.
Describe the null space of B.
It has to contain some non-zero vector. This is true generally for matrices with more columns than rows. I remember seeing something like this on an online resource.
For the moment, let us allow v star to be a vector with real entries, not necessarily integers. Can you think of one which would satisfy the inequality?
How about the origin?
Okay, put v star there. We want to update v star so that eventually all of its coordinates become equal to plus or minus 1. When this happens, we say that the coordinates are fixed. The real valued coordinates, instead, are free. Ideally, the magnitude of b times v star would change as little as possible as we change v star. What would be a helpful direction to travel in?
Well, the null space of B is non-empty, so how about a vector u1 in the null space? That way, after updating v star, we would still have this equality.
Remember that v star needs to be in the cube, so we should instead update v star by finding the largest scale factor alpha, such that where would this new v star be with respect to the cube?
Since alpha is the largest scaling factor possible, some coordinate of v star must be fixed. Geometrically, that means the new v star must be on a face of the cube.
All right, let us fix that coordinate and consider the other two real values. If we take a submatrix B' of B consisting of these variables and the first row, then we can repeat the previous argument, since this submatrix has more columns than rows. Thus, we can find a new vector u2 in the null space of B' and update v star with the largest possible beta such that another coordinate becomes fixed.
What happens to the row we excluded?
That's a good question. Remember that the entries of B and v star are between -1 and 1. Since there are two free variables before updating by beta times u2, regardless of how they change, in the worst case, the inner product can increase by at most 4. The same is true of v2. After updating v star by beta times u2, there is at most one free variable. Regardless of what it becomes, the inner product can increase by at most 2. For simplicity, we can round it to the closest plus or minus 1.
Alright, so we can find such a v star for a 2x3 matrix.
Now it is your turn to consider the general case. Remember, we are given a sequence of coordinates v1 through v lambda minus 1 for the people we will poke. We exclude v1 for parity issues and construct the matrix A with rows v2 through v lambda minus 1. And we want to find a vector v star such that the following holds. How does the argument proceed?
We start at the origin. Move v star in the direction of the null space of A as far as possible until we hit a face of the cube. When this happens, we successfully fix some coordinate of v star. Since A has lambda minus 2 rows, we can fix all but lambda minus 2 coordinates in this way. For the remaining lambda minus 2 coordinates, we will apply the same argument iteratively on submatrices of A, consisting of all free coordinates and all but the last row. These last rows will depend on fewer and fewer floating entries in v star. In particular, when row I gets excluded, there are at most I floating coordinates, so its inner product with v star can increase by at most 2I.
Yes. The theorem that we have proved is that there exists a v star with plus or minus 1 entries such that this inequality is true. Before we proceed, let us try to prove the corollary.
What's a corollary?
A corollary is a result which is a simple extension of a theorem or its proof.
Do we have to go on this tangent? Shouldn't we get back to the actual proof?
Proving theorems is not easy, so we should appreciate extensions which come almost for free. Still, if you're so impatient, I will leave it for you as an exercise.
Great, will do. Okay, we found a vector v star satisfying the inequality.
Yes, but let us not forget about the first row which we set aside.
Oh, you're right. We wanted to show that the inner product between v star and v1 is equal to 0, but that didn't make sense when n was odd.
Consider again the Hamming distance between v star and v1.
v1 was the first node poked, so we wanted its Hamming distance to v star to be at least lambda minus 1.
Is that true of our v star?
It might not be.
Suppose the Hamming distance between v1 and v star is less than lambda minus 1. Could you think of a related node which must be greater than lambda minus 1 away from v1? Pay attention to what the Hamming distance represents.
Well, the Hamming distance between two vectors is the number of coordinates in which they differ. So I guess the Hamming distance being less than lambda minus 1 is saying that the two vectors don't differ by much. That means the antipode of v star must differ from v1 by a lot. Wherever v star is the same as v1, the antipode must be different.
Yes, but make sure to check that we still have our inequality.
There's a corollary, right? In actuality, we have this, which remains the same if we substitute the antipode of v star for v star in the inequality.
Precisely. The proof is now complete, and it looks like we are at the end of our journey. Time to go back to the row space.
Aw, thanks for the assist. Hopefully I'll see you again.
Of course. When you make your eyes bright and eager, we will go on many a strange adventure.